Good. And then I hit a button here.
Perfect. Okay.
Okay.
Excellent.
Yes. What's happening is it's picking up the slides by the camera, not like.
Oh, okay. Okay, sure.
Capture the, yes, the hardware we're waiting for, we'll do it the right way, but.
Okay.
Who knows what that should say? Good.
Should I
Filtering down. Oh,
kind
yeah,
of
you
a
can
walker?
use-
So
Yeah, you may, yeah, so am I. You may as well use that. Right. And let me just turn it on if you're ready.
okay.
Yeah.
Should we turn this? Oh, this is off.
This is on now too.
Oh, okay.
It seems okay to have both of them on.
Okay.
I'll let people filter in.
Hardest talk I gave in my life was when I was on a very small podium and I couldn't walk anywhere. It's like,
Yes, I've had that problem. It's dangerous. Yes. Okay, everyone. I'm very happy that today I can bring you Ankur Moitra. He's really been a leader in synthesizing statistics and computer science and using this to develop theory for machine learning. He is presently the director of MIT's Statistics and Data Science Center, where he's the Norbert Wiener Professor of Mathematics at MIT. On that note, take it away, Ankur.
all right, great. Thanks everyone for coming. So I'll be talking about learning from dynamics. This is based on joint work with some awesome collaborators, Ainesh Bakshi, Alan Liu, and Morris Yao. So today I'm actually going to do my best control theorist impression. I'm going to tell you about one of the basic and most fundamental problems in control theory, which has been studied for over 50 years. But as I'll explain, there are actually wide gaps in our understanding. And my goal today is to give you a new simple algorithm that fills in these gaps. So let me start off by first explaining what a linear dynamical system is. This will be my main object of study in this talk. So a linear dynamical system is described by these two equations. And what it is it's a model for some sort of changing system, which we observe the input and output behavior. So what's going on is that there's a hidden state, which is an n-dimensional vector, and that's changing and evolving over time. And then there are exogenous controls or disturbances that we apply to the system. These are these control vectors ut, we see these. And the trick is that for a linear dynamical system, we don't see the underlying hidden state. We have to try and infer it from data. And what we get instead are these observations yt that are also vectors that have some dependence on, they give us a hint about what's happening in the hidden state. So these two equations, I want to take a few minutes to make sure that we all understand them. So all of the terms in this equation, the matrices, they have a special role and in some cases a special name. The most important of these matrices is the A matrix, that's called the transition matrix. This would describe how the system would evolve on its own in the absence of control. And spectral properties of this matrix are going to play a key role in the long-term behavior of the system. So we'll talk more about that. But there's also this control matrix B that describes the relationship between the inputs we can give to our system and what effect it has on the hidden state. And finally, we have these sensing and feed-through matrices that describe the relationship between our observations, the YTs, and what's going on under the hood in terms of the hidden state and the control vectors. So last but not least, the entire process is not a deterministic process, it's a stochastic process. So we have process noise, which affects our underlying hidden state. And then we have observation noise that corrupts our measurements. So this is what a linear dynamical system is. But especially in Control Theory 101, I want to explain why linear dynamical systems are so widely used, and they show up in so many different areas of application. So in fact, some of the most famous applications of linear dynamical systems are in robotics, navigation, and tracking. In fact, they were used in the literal moon landing, right? So here what's going on is that we have the space shuttle, which is traveling from the Earth to the moon. And we'd like to know the position and velocity of the spacecraft at various times. And the trouble is that we get very noisy measurements of where it is. So instantaneously at every time step, we might have a giant amount of noise. Our estimate, this red circle, might be way off from the true trajectory. But we can hope to use our prior knowledge about physics, about how the underlying system evolves, in order to smooth out our estimates and get a much better estimate of the hidden trajectory. So in fact, this approach is called Kalman filtering. It was used in the moon landing. It won the National Medal of Science back in 2008, so it's an extremely impactful algorithm. But at the end of the day, it's a problem about doing inference in a linear dynamical system. So what would my hidden state be? It would represent all the quantities I care about for my spacecraft, its position, its velocity, and its acceleration. This transition matrix that describes how the system would evolve on its own in the absence of control, this is just a representation of Newton's laws of motion. In particular, it would be an upper triangular matrix with ones along the diagonal. This will be an important structure for later. Because of the way that velocity changes the position and acceleration changes the velocity. So a lot of times you can create linear dynamical systems from discretizing ODEs, exactly like happens in spacecraft tracking. So this is a really fun application. But there are all kinds of other applications, for example, ones where we don't necessarily have prior knowledge about what the underlying dynamics are supposed to be. So there are a lot of natural systems that arise in areas like biology and epidemiology, which can also be productively modeled as linear dynamical systems. So in fact, there's one particular epidemiological process that's been on all of our minds for the last 4 years or so, which is how viruses spread. And you can think about a very simple model, as the SEIR model, where you think about your population as stratified into different groups, whether they're susceptible to infection, they've already been exposed, they're currently infected, or they're recovered. And your state vector just describes how many people in the population are in each of these different categories. And then your transition matrix is just a state machine that describes when and with what probability you transition between these different states. So in fact, the thing that I'm showing right here is from a very recent paper where they do a much higher dimensional version of this, where it's an age stratified version of the SEIR model, so that the rules of how you transition in a state machine depend on which age group you fall into in the population. And they find very good fits to a lot of real world spread. So this is another example of a linear dynamical system in the wild. Let me tell you one more, which is a cool application I learned about from Ben Recht recently. So let's talk about medicine. One of the basic questions you could be interested in clinical applications is what's the efficacy of a particular drug? Now, in clinical applications, the gold standard for what evidence is the randomized control trial. Because you might take some big cohort of patients, and then you randomly split them up into two groups. One, the treatment group you give the actual drug to, and one, the control group that you give the placebo to. And you measure the outcomes in these different groups, and you use this to estimate things like p-values for, what's the chance that the drug is actually effective. But it turns out that in many applications, it's very difficult to create a randomized control trial to begin with. Because you might be interested in a rare disease where there just isn't a big cohort of patients you can construct. Or maybe you're interested in personalized medicine, right? There are a lot of other things like pain medication, where the way that it affects the population is, on average, can be very different than the way that it affects you. And what you really care about is what is the individualized effect on you. So that's called an N of 1 trial, because I only have one data point, which is me, right? And it might sound like you can do nothing because I just have one data point. But it turns out you can do something productive, which comes from understanding the underlying dynamics. Because for things like pain medication, what you can do is on a week-to-week basis, you can randomly decide whether you give them the drug or the placebo. And you can measure the time response of their pain levels. And you can try and learn the underlying dynamical system as a way to understand the efficacy of different drugs, not in aggregate across the population, but on you. More applications, which I won't survey here. You can do things like, there are important applications in speech processing, econometrics, even finance. But let me take a step back. So these were the two defining equations for a linear dynamical system. These are the two equations we're interested in for today's talk. And I explained a little bit about, how these equations arise in a lot of different applications. But when you think about why this is a productive model to study in the first place, there are really two things you want to do with a linear dynamical system as your model. One is inference. If I told you the parameters of the linear dynamical system, I told you the A, B, C, and D matrices, and I told you the covariance of these noise processes. What I could want to do is perform inference on what is my hidden state. I observe the sequence of inputs and outputs. I know the parameters of my model, and I want to form the best possible estimate in a least squares sense of the trajectory of my hidden state. That's what the Kalman filter is doing. It's very powerful. It has all kinds of wonderful, properties that it's statistically optimal, it's computationally efficient, and it was used in the moon landing. But this is really just one of the problems we care about, is when the parameters are known, can we do inference? The thing I'm going to be interested in is really the question that comes before that. See, in a lot of data science applications, we don't necessarily know from prior knowledge what the model should be. It doesn't come from discretizing the ODE or our knowledge of physics. So what happens if, we want to learn the parameters so that we can perform all of these downstream tasks like inference? This is the problem I'll be interested in, is learning linear dynamical systems from data. So what I'm going to do now is I'm going to explain what the main problem is, and first I'll explain it informally. And then we'll try and formalize it, because to make this precise, we have to care about all kinds of things, like how do I measure the closeness of my parameters and the truth? And this is a bit of a subtle thing for linear dynamical systems. You have to be careful with what distance function you use. But I'm going to study the hardest version of my problem that I can, which is I want to learn a linear dynamical system. I want to estimate these matrices, A, B, C, and D, from one single long trajectory. That's it. So just one long trajectory. In fact, in control theory, these things are called controls to use. I'm actually not going to assume that I have control over them. I think it's kind of a misnomer. I'm just going to assume that they're disturbances. So you can think of these as being like Gaussian random vectors. They don't even need to be Gaussian. They just need to have bounded moments. You should just think of these as random things that affect my system. Yeah.
Shouldn't I be worried? Because the control question is also very much influenced by these. You may have a target of behavior.
Yeah.
But to get that behavior, you need to know the parameters. You don't know the parameters, so you need to estimate. So if you're not including the rules of choice of control in the story, it might mess up the appropriateness.
Right,
of your
that's right.
study.
So the learning problem is a bit subtle, because if I'm really allowed to choose any U's I want, and I could make them gigantically large, then you can actually trivialize a lot of the learning problems. And
But you won't control very well.
Right, that's right. So I'm going to study the version where these are actually obliviously chosen for me. And we'll see in the course of the talk that I need very little assumptions about what these are. So I'm just not even going to assume that these are in my purview to choose.
Okay.
But if I'm allowed to choose them, you could obviously do even better. But very good question. Okay, so what was I saying? So the important thing is that what I observe is the sequence of the inputs and the outputs. And I'd like to infer these A, B, C, and D. And one of the questions that I need to answer in order to make this precise is I need to tell you, in what distance, in what norm do I want my estimates to be close to the ground truth? See, this turns out to be kind of a little bit of a subtle issue. I'm actually going to take the strongest possible definition, which is I'm going to say that two linear dynamical systems, one given by parameters A, B, C, and D, and the other given by A hat, B hat, C hat, and D hat, are the same if they always produce the same behavior. So if for any sequence of adaptively chosen inputs, this UT+1 depends in an arbitrary way on whatever has happened so far in terms of the observations and the inputs, if those two linear dynamical systems generate the same distributions on their trajectories. So this means that the linear dynamical systems are functionally equivalent because they act the same in terms of their input-output behavior. See, the part which I'm not going to prove, but I'm just going to assert, is that two linear dynamical systems with Gaussian noise are equivalent if there's a change of basis in which they're the same. So the point is I never see the hidden state. So there's always a way to rename the hidden state in such a way that, it doesn't affect the behavior of the inputs or the outputs. And that's exactly what this proposition is doing. Because if instead the hidden states were, some transformation according to you, I would just undo that transformation when it comes to my observations. So I'm not going to prove this proposition. It's a very easy proposition to prove. But what I claim is that this defines my appropriate notion of parameter distance. This is what it means for two LDSs to be equivalent. And what I'm going to want to do is to try and learn estimates A hat, B hat, C hat, and D hat that are close in this metric, such that there exists a transformation U and they're close after applying that change of variables. So here's my formal problem. I'm given one long trajectory with the sequence of inputs and outputs, and I want to find A hat, B hat, C hat, and D hat, such that there exists a transformation U, so that after that transformation, A and A hat are close in Frobenius norm, they're at most epsilon off, and the same for B, C, and D. So this is my formal problem. So any questions so far?
Yeah. Others.
Okay, yeah.
Is it really the Frobenius norm that would control this kind of distance of resulting distributions that you were talking about?
Yeah, so, for all these things, what you could do is you could ask, what's the, I could look at something like spectral norm, Mahalanobis, whatever you want. And you could ask for like tighter rates, and that would depend on how you choose the norm to measure closeness. But, here we have like a very big open problem already, which is shockingly, despite the fact that this has been studied for 50 years, it's not just that I don't know an algorithm. I don't actually know sample complexity guarantees that are polynomial in all of the relevant parameters.
So this, I guess, is kind of a weak form, right? Like spectral
right.
norm would maybe be a more kind of stability.
It could be,
preserving,
we can get into that offline. A better way to do it is to like measure some sort of TV distance between their input-output behavior. But I'm going to keep it simple for this talk. Yeah.
Oh, yeah. Just a question. So the output should be identical, or the distribution of the output?
Well, I just want A hat, B hat, and C hat, and D hat to be close to this distance. And what I claim is that if I'm close enough in this distance, it has a functional interpretation in terms of the input-output behavior. But this was just my motivation for this distance. Because a lot of times you might trivialize the problem or make it impossible if you choose the wrong distance. Yes?
So there's another issue here. Right now, this is looking like a batch learning problem.
Yeah.
But in control, you would very much like to learn as you go.
Yeah.
So you would want an online learning formulation of this.
Right.
Are you going to do that, or are you going to stick with the batch?
There are versions of it that follow from this, because what will happen is that you have some burn-in in your long trajectory. And then you learn, good enough parameters that you can take the optimal controller for that and then deploy it, and then you'll get some regret guarantees. These are subtle questions because even in fully observed systems like LQR, there's some very nice work of Ben Recht and company. And the issue is that, even if you have an estimate of the parameters, you actually have to create some confidence intervals around your estimate such that, the controller you apply is good across the entire range. Otherwise, you don't have any safety guarantees. So, for our problem, even this question is wide open, but there are tons of later questions we could ask like that. And so I can talk about those a bit later. All right, great questions. Any other questions? All right, so I'm gonna, yeah.
How much easier is it to have multiple? Because also
I'm gonna table that question for later. That's a very good question. We'll get into that later. I don't want to answer it now. All right, so there are maybe 5,000 papers on learning linear dynamical systems. And it's kind of this wild west of different assumptions that are out there. So in the early days of control theory, the results people had were mostly non-asymptotic things. And recently, for reasons I will explain later, people got reinterested in them in terms of getting, effective bounds on the running time and sample complexity. And I can't explain all of the assumptions that go into these 5,000 papers, but there's one assumption that shows up in virtually every single one of them. That's a very bad assumption. So what I'm going to do is I'm going to explain what this assumption is, and then I'm going to convince you it's a very bad assumption. It's an assumption that's called strict stability. So I told you one of the keys is the transition matrix A. That describes a lot of properties of the long-range behavior of the system. When you look at the spectral radius of A, namely the largest absolute value of any eigenvalue, if the spectral radius is strictly less than 1, you call the system strictly stable. And if it's less than or equal to 1, you call it marginally stable. Virtually all of the papers that are out there assume strict stability. And even though it sounds like a slight difference, I claim it's very fundamental and it captures something conceptual. See, first of all, strict stability, I claim, fails even in simple cases I've already talked about. You remember in the moon landing example, the transition matrix was an upper triangular matrix with ones along the diagonal. So it definitely has eigenvalues equal to 1. It is not strictly stable. And when you discretize some system, that's often what happens is you don't have strict stability. It's just an unreasonable assumption to hope for. See, what's really going on is that when I impose strict stability, I have no long-range correlations. If I told you my hidden state at some time step, like the initial time step, and asked you what that told me about my hidden time state at a much later time, that would vanish and go to 0 because I'm taking higher powers of my transition matrix. So in effect, you have no long-range correlations. And that means that even though in principle you have only one long trajectory, you actually get as many trajectories as you want because you can just wait long enough until the thing mixes, right? Now, marginal stability is really just an assumption to prevent the system from exploding. Because if my spectral radius were larger than 1, the magnitude of my state vector would be exploding. And then adding a fixed amount of noise doesn't really make sense. So it's really the scaling that makes the problem well posed. But to be concrete, if you stare at all these papers and look within them, they have all kinds of other assumptions too. But one of the things you'll always find is that the bounds in terms of the running time and sample complexity look like 1 over 1 minus rho of A. And this is not a mystery. This comes from mixing. This is a mixing condition. Yeah.
For the example of the COVID system,
yeah,
that's actually unstable when it's like exploding. Could your method not work for like that part of the COVID estimation?
So it explodes for short time steps, and then it doesn't.
Yeah.
So that's one of the things is that even the eigenvalues govern the long-range behavior, but you can actually explode the norm for a little bit, and that has to do with the conditioning of the system. Now, conditioning will show up, so we'll see that in a minute. But really, I claim that there's a conceptual question here, which is, do long-range correlations, the kind that necessarily occur when we have marginal stability, do they obstruct learning? And I claim, and I'll just make this assertion for later, that it turns out that strict stability trivializes the problem. So I'll make all that precise. Okay. All right, so I just told you what assumptions I don't like. Let me tell you what assumptions I do like, because you do need some assumptions in order to learn the problem. The nice thing is that the assumptions I'm going to tell you about are things which are close to minimal. They are things which you can prove are needed in some appropriate sense, which I'll explain. But they also go back to the founding of control theory. So one of them is called observability. So what you do is you create this block matrix. Remember, A is my transition matrix. That's very important. And my C matrix is the thing that describes the relationship between my hidden state and the observations. So I create this block matrix that's C times A squared, and so on, out to some order, S. And this is called the observability matrix. And what I claim, this goes back actually to Kalman, if this matrix does not have full column rank, you're dead. So why is this? This is just a simple exercise in interpreting what these matrices mean. So imagine that this matrix does not have full column rank. Then if I move the state in some direction, Z, which lives in the null space of this matrix, I claim I don't see the change. So, if I look at xt plus Z versus xt, well, because Z is in the kernel of this observability matrix, that means it's in the kernel of C. And that means that if my state was xt versus xt plus Z, I can't tell on my next observation because C doesn't see it. Not only do I not have an effect on the immediate response, but I don't have any effect on the next response either because it's in the kernel of C times A. It's the kernel of C times A squared. And what this means is that I don't observe the change even over S time steps. So what Kalman originally proved was that if this matrix does not have full column rank for infinite order S, then the problem is information theoretically impossible. And there's a dual version of this too, which works in exactly the same way. I can create another block matrix, which is called the observability matrix. Controllability, thank you. The controllability matrix. So this is B, AB, A squared B. And if this matrix does not have full row rank, what it means is that there's some portion of the state space that the control cannot push me in. There's some direction which I cannot create movement in, even if I choose the right control. So the proof works the same way, and the necessity of these assumptions goes back to Kalman's original work in 1960. Yeah?
So, if that's it, if that part of the state space is not useful for learning,
well, so this comes down to there's different notions of learning. So one of them is parameter learning, where I want to find a set of parameters that creates an equivalent system. Another would be proper density estimation, where I just want any other LDS. And in that case, which has the same input output, types of things. I mean, you can weaken the goals in the case where, these assumptions aren't met, but you have to change the metric which you want for closeness. So somehow parameter learning is usually the easiest one of these to do. So what I claim, and I'll give you, the key ideas in the proof, is that there's a polytime algorithm for learning even under marginal stability, just under controllability and observability. Now you can't assume that they're just full column and row rank respectively, because you need a quantitative bound. So you need a lower bound on the smallest singular value. So in particular, you can just assume that we have condition number bounds on these matrices. And what I claim is that we'll have an algorithm that's even polynomial in the condition number bounds. And then moreover, you can prove an almost converse to the statement that if the observability and controllability matrices are ill-conditioned, exponentially ill-conditioned, for all orders S, then the problem is actually information theoretically impossible. So the difference here is I'm assuming that there's an upper bound in the condition number for some order S versus the lower bound is for all orders S.
So what's the relationship between the time t and the condition number so that we could get consistent estimation?
Consistent estimation of the parameter. I mean, what's the rate?
Yeah.
What's the rate?
It's not necessarily rate, just something that's epsilon, you were thinking about over here, right?
Yeah.
I guess, okay, what's it, it's naturally there will be relationship between your t and your, condition number over here.
Right. So you're thinking of capital T, which is like how long my dynamics goes.
Yeah.
So here we're going to get, the rates will be polynomial in everything. The dimension, the condition numbers, and 1 over epsilon. Now the dependence on epsilon will be suboptimal. It'll be 1 over epsilon to the 4th, but I'll explain where it comes from. And I'm not actually going to go into that granularity in this talk, but that's a good open question. Okay, yes?
I'm sorry, I think in the previous slide you said the inverse, you're kind of showing it's information theoretic important.
Yeah.
Is it like a computational inverse too that is exponential?
No. I mean, but here, if you can't do it information theoretically, you can't do it computationally.
Yeah.
And really this issue about whether there's an order S or it's for all orders is kind of a bit of a technicality because, it could become well conditioned when you go up to 2S and then you could just try out your algorithm there. So I think there is a bit of subtlety here, but, that's why I'm just calling it a somewhat converse. Yeah.
I'm wondering what happens if you have some kind of sparsity in this model. For example, some states are silent and never.
Yeah. Look, you guys are asking all the right questions, but my goal here is to say that, there is this dictionary between what we know and love in static learning theory and what happens in the dynamic case. And I'm just trying to solve problem 0. So all of your questions are great, but we will get to them later. And the thing I want to convince you of is that there's a dictionary. So let's do that first. Okay, we good? All right, so there is one paper I know of that doesn't have the strict stability assumption. It's a very nice paper of Simtrowitz, Bokar, and Recht. Unfortunately, they give an unspecified dependence on the system parameters, things like the dimension of the system. So you can check that their bound really does turn out to be exponential, even in cases where you don't need an exponential dependence, and we'll get polytime guarantees that depend on the sample, the condition number. And also I wanted to make one more philosophical comment. So, I told you that there was this huge interest in linear dynamical systems, in the early days of control theory. And then it sort of, had a bit of a lull, and then all of a sudden there was an explosion. What happened? So one of the things that happened was we got interested in things like recurrent neural nets, which are nonlinear versions of these problems. You have a nonlinear dynamical system. And of course, we want to know when and why they work, but how the heck are you going to prove anything about fitting a nonlinear dynamical system? So what people did was they analyzed gradient descent on linear dynamical systems as a metaphor, as a prototype. So maybe we can't analyze training dynamics on full recurrent neural nets, but maybe we can understand how they behave in terms of things that are more tractable. But I would argue that this is really putting things out of order, because when you try and study the problem as a metaphor for something that's happening empirically, you might not actually understand what are the fundamental limits of that problem and the learning problem to begin with. And I'll explain that all of these works, except for this one, have the strict stability. And I'll show you that strict stability makes the learning task trivial. So this is my bit of philosophy, and we'll get to that. Actually, I guess I have one more bit of philosophy before I do that. So, what I'm going to do instead, right, of gradient descent on a non-convex objective function is I'm just going to go back to what's our tried and true playbook. I've spent a lot of time, giving algorithms for learning in a lot of unsupervised learning contexts. And there's this blueprint that's very important and powerful, and it goes back to Carl Pearson in 1894. And all you do is you follow this simple step. You're trying to learn the parameters of some distribution. You take samples from the distribution to estimate moments. You use those empirical estimates of the moments to set up a system of equations in your unknown parameters. And then somehow you solve those system of equations and try and prove that your estimates are good. Now, Pearson didn't prove any guarantees about his method. But over the last 15 years, there's been a huge amount of progress on proving guarantees for the method of moments. You can use it to prove things like algorithms for learning mixtures of Gaussians, for learning hidden Markov models, topic modeling, robust estimation. This is just our standard playbook in terms of giving algorithms with provable guarantees, both in terms of algorithms and statistical complexity. And I'm a simple guy. All I want to do is I want to figure out whether there's a version of the method of moments that works for non-stationary data. This is the start of having a dictionary between these things. So here's what my blueprint will be, okay? First, I have to talk about what the moments are. It'll be another block matrix. It's called the Markov parameters. It's D, you can just ignore D for this talk, CD, CAD, CA squared B, and so on. What this describes is the input-output behavior of my system. And I'll explain why that's true later. But here's my recipe. I'm going to estimate the Markov parameters from samples. And then I'm going to use the Markov parameters to estimate the actual parameters I care about. That's how I'll get my estimates A hat, B hat, and C hat. Okay? And not only am I simple, I'm also lazy. So in fact, I claim that step 2 has already been done for us. It was done in the 60s. And it's called the Hoek-Kalman algorithm. And I'll prove this proposition for you, that if you are given the Markov parameters, that you can learn the actual parameters that govern the system. And I have to confess, I tried to read this paper, the original Hoek-Kalman paper, and I couldn't make any sense of it. So I'm just going to give you a different proof. Because I think there's a more fun proof that parallels a lot of what's happening in tensor decompositions that I think is probably the right way to think about it. So remember, we're in step 2. So if someone gave me the Markov parameters, we'll have to figure out how to find those later. And that'll be where the new ideas are needed. But I'm going to take these Markov parameters and I'm going to arrange them into a Henkel matrix, a block Henkel matrix. So the top left thing will be this matrix CD and then CAB, CAB, CA squared B, and so on. You shouldn't yet see why this makes any sense, right? If you do, you should probably see a doctor. But let's get to that in a second. I have one more piece of notation, which is when I remove the last column in my block matrix, I'm going to call that H1. And when I remove the first column, I'm going to call it H2. So this is the notation I need to describe the whole column. I'm going to take my Markov parameters and I'm going to arrange them into certain block matrices. And there'll be a spectral problem on these matrices that's going to recover my parameters.
Can I interject momentarily? Are you going to explain why those things you call the Markov parameters are the Markov parameters?
Yeah, but later.
Later. Okay.
When we estimate them.
That's fine.
Okay, so for right now, we'll just take them for granted, but let's give the first hint about why this makes any sense. See, I told you the two key matrices we care about are these observability and controllability matrices. O is this matrix C, CA, CA squared, and so on. Q is this matrix B, AB, A squared B, and so on. Well, what I claim is that this block Hankel matrix H that I constructed can be written as the product of observability and controllability. That's just from the definition. So this gives us the first hint that this makes sense, because I know the left-hand side, right? Someone gave me the Markov parameters, I can construct that H. And now the thing which I'm looking for is somehow an unknown factorization of this matrix. So what I'm going to do is I'm just going to find any old factorization of this matrix and then prove to you that it's equivalent. So what should I do? I should use my favorite tool, the SVD. I'll take my H1 matrix and I'll write it as U times sigma times V transpose. That's not the product of two things. So I'm just going to split up sigma into two pieces. And then I will group them together and I will suggestively call the first part O hat because I want it to be O. And the second part Q hat because I want it to be Q, right? But now, the key point is that just like H was the product of O times Q, so is H1. It's just that you change the orders because I removed a column, right? And so the fact that this one matrix is both equal to O hat and Q hat and O times Q, well, tells me that if these matrices O and Q have full column and row rank respectively, there's no choice, but they must be related by an invertible transformation. If this were not true, you could not have the right row rank for your matrix H1. So this is just a basic fact in linear algebra that, if these terms in this factorization have full column and row rank, then they are related, right? And now I'm off to the races because, I have my O hat and Q hat that came from taking the SVD of H1. And now I just have to figure out how to estimate my transition matrix. So what I can do is I can take H2. That always had at least one power of A, so it's O times A times Q. And now when I use what I knew from step 2, that O is related to O hat, Q is related to Q hat, up to this transformation by T, I can left and right multiply by the pseudo inverses. And what that does is it strips off the O hat and Q hat. That gives me A hat up to the same similarity transform, up to conjugation with T. So that's the proof of the Ho-Kalman algorithm. I think that's what's in the original paper, but I can't be sure. But this is a proof, right? And so then, in reality, whatever I do for step 1, no one's going to perfectly give me the Markov parameters because that'll be subject to sampling weights. So really, there's a slightly stronger statement I need, which is that the Ho-Kalman algorithm works even if I'm given noisy estimates of the Markov parameters. This was only done recently, a couple of years ago, in a paper of Oymak and Oze. It's a nice paper, but it is quite intuitive, right? Because the key point is how stable is the SVD? That was the action that was happening in the Ho-Kalman algorithm. And the point is that the SVD has stability properties when those O and Q matrices are well conditioned. So you can back out some bounds just from using matrix perturbation theory in the context of the Ho-Kalman algorithm. But this is all known stuff. And now we get to the heart of the problem. And I want to emphasize that this is different than our usual playbook in the method of moments. See, now I still have to figure out how to estimate the Markov parameters from data. Usually when we do the method of moments, estimating the moments is the easy part. But here it's going to be the hard part because of the dynamics of the LDS. So now I'm in the phase of the talk where I have to make good on the promises that I made. The first thing I'm going to do is I'm going to answer Andrew's question. Why are the Markov parameters the input-output behavior? Because they satisfy this condition. So what I claim is that one way to think about where the Markov parameters come from is I look at the input at some time step little t, and I look at the time-lagged output, y sub t plus j. And let's just assume that the control and noises have identity covariance. If they don't, you can just correct this based on whatever their covariances are. But in that simple case, I claim that as you change j, you sweep out and you get the different Markov parameters. Now, once I assert this for you, there's only one way to prove it, which is to expand the recurrence, right? So let's do it for j equals 1. I take y sub t plus 1 and I write it out. I don't see any UTs here, so I expand my xt plus 1. And then I have it UT. And then the covariance with UT all goes away other than that CB term, right? And then if I did this for other values of j, same proof would work, right? So now let me convince you that, I'm done, except for the fact that I'll be lying, right? So now it sounds like we're done, because I told you that when I have the Markov parameters, I can use Ho-Kalman. And I gave you an unbiased estimator for the Markov parameters. So what do we usually do with unbiased estimators? We add them up and we average, right? So this is an unbiased estimator for this Markov parameter. And that's true independent of what the value of little t is. So let me add them up over different time steps, and that should work, right? I guess we're done. Oh yeah, that's right. That's the entire problem, right? Yeah, that's right. No one told me that this is actually decreasing the variance. In fact, that's the whole point of what a linear dynamical system is, what makes it challenging, right? And now I can make good on my other promise. When you have strict stability, the problem is trivial, right? When I have strict stability, I do get independent samples. I can just wait long enough until I mix. And then I can average them, and the variance really would be decreasing as I add more and more of them together. So the entire time where we were writing 5,000 papers on gradient descent for learning linear dynamical systems as a metaphor for what's happening in recurrent neural nets, we hadn't realized that we trivialized the problem because there were no long-range dependencies. That's kind of funny. But let's try harder. So let's try to figure out how to correct our estimate. So now we're going to use ideas from control theory. Because really the problem was that my system was unstable. So what I'm going to do is I'm going to stabilize my moment estimator. So is there a way to create a new time series? Can I engineer a time series, y hat t? That depends on some coefficient Cj that just has to do with how I create this time-lagged linear combination of the responses. But what I want is that, first of all, this new time series I've engineered is still good for my estimation task. It should still give me an unbiased estimator of the Markov parameters. I don't want to change that because that's what I want to solve, right? But I also want that a good choice of the CJs makes the variance of this estimator be bounded independently of t, so that it's not exploding. So those are my two goals, right? And now the beauty of it is that, I can pretend I know the LDS when I guess a good choice of the CJs. Because then I can hope, once I know that they exist, that I have convex programming tools to find them. So we'll go through, a few attempts to explain how this works, in stages. This first one is the most important one. This is the thing that when you see it, convinces you that it ought to be possible. So let me take CJs, which are the coefficients of the characteristic polynomial of A. All the action is happening in A. And I claim that if I did this, things would be nice. So the key fact is the Cayley-Hamilton theorem, which tells us that every matrix satisfies its characteristic polynomial, or to put it more conveniently for us, a high power of A to the n, it's an n by n matrix, can be expressed as a linear combination of lower order powers. And that set of coefficients I need are the things that show up in the characteristic polynomial. And what I claim is that if I did this, if I engineered a time series using the characteristic polynomial, the CJs, I would actually cancel out all but some small number of transient terms. So again, once I make this assertion, there's only one way to prove it. I tried to write out the full equation on my slides, I couldn't. Then I simplified it, I still couldn't write it out. So let's just get rid of almost all the terms because that's where the action is happening. Let's pretend that my two defining equations for the LDS were just these two equations right here. So I'm getting rid of a bunch of matrices and noises, but all of that stuff works the way you'd expect. And let's take my engineered time series, these y hats that depend on the CJs, and let's collect terms. So I can expand the y's in terms of the x's. Now I can organize them into a table because ultimately I care about where the UTs show up. And I can play the same game where I take this term right here and I expand it into a UT and an XT. I can take these two terms right here and I can expand them into a UT minus 1 and an XT minus 1. And when I keep doing this, the key point is what's happening in the rows of this. I have higher powers of A being canceled by lower powers of A, right? So there's no hope of creating cancellation here. This is a transient term. There's only one term that involves UT. But far enough down this table, eventually I get cancellation. So I cancel out all but some polynomial number of transient terms. So when you do this, you get an expression that looks like this, just in the simple case that we're talking about, where I simplified the LDS. And this is what I mean right here, is that when all these other things go away, I only have a polynomial number of terms left over. So my system is not actually exploding off to infinity anymore, like we normally do with marginally stable systems. So that's good, I solved the problem too, right? I made sure that the variance of my estimate with this engineered time series using the characteristic polynomial is bounded independently of t. The trouble is that I broke property 1, right? So if I just look at the expression I had on the previous slide, I not only have this Markov parameter, but I have linear combinations of other Markov parameters showing up. So when I look at the correlation between yt and ut minus I get not what I'm looking for, but some other terms too. So here there's a very simple fix, which is just instead of immediately using the previous terms to create cancellation, just wait a little bit. What happens if I wait using some lag? The point is that if I wait r time steps and r is larger than k, then there is no ut minus 1 that shows up here because it hasn't even happened yet. There's no ut minus 2, there's no ut minus k. So I can still hope to create the same kind of cancellation, not using characteristic polynomial, but something else, with the property that I don't change any of a small number of these Markov parameters, enough so that I get the Ho-Kalman algorithm to work. All right, so you still cancel out long-range dependencies, and that takes us to our third attempt. This is a bit strange because we only had 2 problems, and it seems like I fixed both of them. There's a different problem, which you probably didn't see, which is that I lied. I lied to make it a bit easier. So the trouble is that no one told me that the coefficients of the characteristic polynomial are bounded. They don't need to be. So it turns out that what you do is you don't treat CJs as coefficients, you treat them as matrices. And what you really care about is how you regress, future observations against things that happened in the past. And that's again where the condition number of the observability and controllability show up. So if you do this the right way, the only thing you need to show the property you need to show existence of good bounded CJs that are now matrices is really the same property that showed up in Ho-Kalman and all the other things. It's this condition number of observability and controllability. So this gives the overall architecture of the proof, right? Or at least most of it. Yeah.
Quick question. Is there any easy way to understand why the regression would give you the good CJ?
Why what?
Why the regression would give you the good CJ? You do regression, right? YT, against the previous iterations.
Yeah.
And then you do some kind of screw, I guess. And then, okay, they have a solution. Why that solution would be a good
This is the simplest way I know.
Oh, okay.
Yeah. Because ultimately, for the regression, you have to show that there is a good choice of the regressor that's bounded so that you can control its risk. And what I really gave you was a proof of feasibility. Now I'll do that in a second, right? Because it sounds like I have the proof, right? But the trouble is that I'm really, things are a bit backwards right now because my goal was to learn the Markov parameters, estimate them from samples, and to stabilize my estimator. And here what I'm arguing is that if I knew the observability and controllability matrices, it would imply the existence of good CJs that meet all my conditions. But I don't know the observability and controllability. So really the way to think about it is in terms of a convex program. What I really argued for you was feasibility. So what I want is I want to look for some choice of the CJs, we can still pretend they're coefficients for right now, that have the property that they're small, they're not too big, and yet they stabilize the empirical time series. And what you want to then show is really the soundness property. Once I know feasibility, which is the thing I really just reasoned about, soundness asks like, why any feasible solution of this convex program has to yield a good estimate. And really this comes from the same types of arguments I'm giving you. So if you imagine some choice of the CJs, not just a good choice, like from the characteristic polynomial, you can create a potential function that tracks how much variance you have not canceled out. The point is that if you haven't well canceled out the variance, then you won't meet this condition. And that comes from some type of anti-concentration argument.
There may be some type of the second group.
Yeah.
You have K on one side, and you see in K.
Sorry. J. Thank you. There are indeed typos there. Thank you. Yeah. Okay, perfect. So this is, it should be J for the subscript. Yeah.
So I think also so all you know is K, essentially the dimension of the system you're looking at.
Yeah.
How do you get S?
S has to be given to you for this. So, there are tricks you can play with, like if S is not given, you can try a bunch of different S's. But keep in mind, where am I, the simple version of this, I'm using knowledge of S to figure out how far back I should go in engineering my time series, right? And then, what I'm doing is I'm using, that also to determine my lag. Because ultimately S gives me the order that I create this Ho-Kalman algorithm, and I have to estimate enough Markov parameters. The tricky thing is that, if you didn't know S, it would actually be very hard to verify what value of S the observability and controllability become well conditioned if you don't actually have the parameters. So I think that that's a non-trivial question. Yeah.
I really like the idea, secure idea, to analyze method moment. And after you have done this, can you get similar result for this way? That's
Right.
kind of a typical way people do it.
Yeah. So let's do the list of questions that one would want to do. That's a great one. I don't have that one down. But the next thing you would do is instead of, in this Simchowitz-Bokar rect thing, they have some oracle inequalities. Really, the point is that you need an argument for why the oracle bounds are good. And really, this should be the proof. So that's the type of thing you can do, is you can then use it to analyze least squares, right? So that's one question. But there are all kinds of other things because really there is a dictionary. You guys were asking me all these questions that should be in this dictionary that's to come. But we're not there quite yet, right? So you asked me about sparsity, about proper density estimation. There are even other questions I can ask, right? So another neat one is like, in statistics, there's change point detection. So I'm flipping a coin and it's got bias P, and then at some point it switches to bias Q. So I'd like to localize, when that switch happens. And the key to getting good bounds on where that change happened is, having good enough confidence intervals around my estimates. Because what you do is you take some empirical average in a window, and when that's far enough away from what it used to be, that's when you say the change happened. You can ask the same types of things for LDSs. What about change point detection for LDSs? Like when the virus changes, right? So there, the prerequisite to doing change point detection is to be able to learn a linear dynamical system to begin with. But once you can learn it, you can hope that if I have good enough confidence intervals around its parameters, I can use it to do change point detection, because I could only use the data in some time window and then study when the estimates stop being good or they start changing. There are also versions with heterogeneity. So you can ask questions like, what happens if there's not one time series, but there's a mixture model? Actually, the reason I gave the Ho-Kalman the way that I did was because it's connected to this other tool in learning theory that we know and love, which are called tensor methods. And really, you can think about the Ho-Kalman algorithm as being a type of block tensor method. But then you have these very natural routes to go, which is, with mixture models, you can look at higher order tensor methods. And that's exactly the kind of thing you can do. You can get algorithms for learning mixtures of LDSs, which work even when the trajectories are not geometrically separated, but work under much tamer conditions. And I'll briefly say that there are a lot of connections to RL, but maybe that's a topic for another time. So let me just stop there and tell you what I hope you got out of it. So I introduced linear dynamical systems. I told you why they're so prevalent and why they show up in all these different areas. But I told you that there is this one, shockingly wide open question about learning LDSs from data. And then I showed you how there's a new algorithm based on the method of moments that can solve this problem. And I'm really excited about this more general question, which is, maybe all of the tools we've been discovering in the context of theory ML about how to reason about the method of moments have a new life in contexts where the data is not stationary. So I'll stop there and take any further questions you guys might have.
And so at one point, you assumed that the noise had identity covariance.
Yeah.
If it does not, do you need to know the covariance?
No.
Okay.
Yeah. So it turns out that it's just the equivalence changes because the equivalence in terms of the parameter distance is really only if I have identity covariance noise. Otherwise, you have a weaker notion of equivalence, and the change happens in the noise.
Okay.
So you don't actually need to know the noise. It's just it changes the parameter distance.
Here, the sort of ways of constructing facts. I have this initial learning chunk of time where UTs are just like I draws.
Yeah.
And then I learn my ABC and then I run Kalman.
Yeah, that's right. But actually putting those two pieces together isn't entirely obvious because for the learning goal, the goal is to find some parameters that are close. Now, the issue is that there's no guarantee that the Kalman filter you find on the parameters that are close is also a good controller for the actual parameters. So these are subtle issues even with full observability. And these are things which people have studied in the context of LQR, but that's exactly the next type of question, is that you need some sort of bound that you can search not just for the best controller for the system, but the best controller in some set of feasible systems. Yeah.
So you have a linear system, but the description more precisely of the laws of motion of an aircraft involve signs of angles instead of the angles themselves. So there's, you need to angles of change of motion that's very small to have a reasonable linear approximation.
Right.
So can you discuss the extent to which what you've been teaching us today extends beyond the linear regime or approximate linear regime?
Well, okay, that's a good question. I mean, even when you have so the question is how fine-grained your measurements are, because in short time scales, these are very good approximations of the system. One of the things that people did study back in the day in control theory is really, when the parameters of the system are known, what happens if you're doing Kalman filtering with intermittent observations? So there's a whole theory of how finely spaced you need the measurements to be in order for the Kalman filter to actually, stabilize the system. This is stuff that Mike Jordan and company did back then. So I don't know offhand what the quantitative things are, but some of these issues you're bringing up are probably teased out in these intermittent observations.
Plus one technique, maybe a little bit technical stuff, is in the convex optimization.
Yeah.
We are still keeping this time lag for estimating a group of C.
Yeah.
But actually the time lag does not correspond the estimation of C. Even you keep R to be 0, it still gives your estimation of C.
Right, but
what's the
see,
reason?
okay, so but the point for the time lag, right, is that, you know, the longer I time lag, the more estimators of Markov parameters I don't corrupt. Because then there was no previous U that showed up there. So really the order is like, you know, once I decide on my Ho-Kalman algorithm for how big that Hankel matrix is, that governs what my lag needs to be.
And for convex optimization to estimate the C,
Yeah.
you need to keep the same R as the Hankel matrix.
No,
So
you can
any
choose,
R.
yeah, that's,
So you seem to be drawing this parallel between this Ho-Kalman algorithm and the Genrich algorithm.
Yeah.
Is that right, from tensor decomposition?
That's
So
right. I didn't say generic, but yeah. that's right.
right, but there's no kind of implicit tensor really. So are you saying that
Because
like
tensor
that-
methods are generalized eigenvalue problems, they're just called tensor methods.
sure, so that one kind of ingredient of the Yenrik algorithm is just giving you some guarantee that it's kind of a simultaneous
That's right.
diagonalization.
That's right.
thing. Okay.
So that's why I like this version of it,
I see.
because then you can ask, you know, whether you can do simultaneous diagonalization on like flattenings of higher order tensors, but still have them, you know, be the analog of like higher order generic.
But so this thing you were saying at the end is that maybe if you actually have kind of higher moment data, you can still
You
do
can.
a similar
That's
approach.
right, you
Okay.
can. Yeah, I didn't talk about it, but you can.
No more questions? Thank you very much. We're lucky.